I'm on this page right here, and it says logarithmic energy decrement with a pretty cool graph on the bottom. So here's the uranium pellet. And we know a fission event occurs and a neutron is released in that pellet. Now, that could show up within 10 to the minus 14 seconds. It could occur at 2 seconds, all the way out to, on average, for a delayed neutron, that neutron could be released in 12.7 seconds. Then we know it's going to travel through the pellet. I know that there was a helium gap here, and then there was the clad, and then there was the water out here. Our moderator, the thing that we use to slow down or thermalize the neutron. Well, we know that when a neutron comes here and it sees hydrogen in the water, it's going to scatter and give off energy. So some of its energy is going down. It is thermalizing. How much energy it gives off is key. The more energy it gives off, the less collision or scattering reactions that would be required till this thing became fully thermalized. So we have this thing that we call the average logarithmic energy decrement or decrease, decrement per collision. How much was the average loss of energy per collision right there? A neutron banging into that water molecule, giving off energy because it has about the same mass of hydrogen in that molecule. And we refer to this as squiggly E. That's the symbol for the average logarithmic energy decrement per collision. You should be able to draw a conclusion. As the average logarithmic energy decrement per collision goes up, the number of collisions required to thermalize goes down. That's key. Let's take a look on this page. It says the ideal moderating material, the ideal thing that we use to slow down our neutrons should have some certain properties. It should be able to scatter really well, so it should have a high scattering cross-section. It shouldn't absorb the neutrons. It should have a small absorption cross-section. I don't want the moderator to actually absorb it. I just want it to slow it down so that it can get reabsorbed in another pellet of uranium. And then the last thing it says is it should have a large energy loss per collision. We refer to that as the average logarithmic energy decrement. It is the average decrease per collision in the logarithm of the neutron energy. So we'll just be looking at the exponent rather than the number itself. And we call this, with a symbol of that, squiggly E, which really means average logarithmic energy decrement. What's really cool is you can kind of see, here's prompt neutron birth energy way up here, around 1.82, somewhere up there. And then it's going to start giving off energy, number of collisions. Look at the difference right here. Delayed neutron, born at a less energy level. It's going to have 1 or 2 less collisions than a prompt neutron because it was born at a lower energy level. And this, each time, these are collisions occurring. We can determine with this equation right here, the number of collisions. The number of collisions before I become thermal is going to be equal to, well, the natural log, that's just going to be a button, and take the high energy versus the low energy that I'm going to. So this is a starting point and an ending point in terms of energies, divided by this squiggly E, or the average logarithmic energy decrement. And we know as the logarithmic energy decrement goes up, the number of collisions would come down. But let's put some numbers in there and crunch them. I think we said the average energy level of a prompt was 2 million electron volts. The average energy low, fully thermalized, was what, 0.048 electron volts? That's EV. So take 2 million divided by 0.048, depress natural log, and for our purposes right now, we're going to say that the average logarithmic energy decrement is about 1 for our moderator, which is just regular water. If you'll do that, Then also do it for the high energy of a delayed. So this would be the prompt energy starting and ending point. If we did it for delayed, the only difference is I would put 0.5 mega electron volts right there. Divide it by 0.048. And if you'll do those, crunch those on your calculator, 2 million divided by 0.048 natural log, then 0.5 or 500,000 divided by 0.048 natural log, you're going to see the difference of about one collision between a prompt and a delayed, due to the prompt is born at a higher energy level, and it's going to require one or two more collisions to get fully thermalized. That's pretty cool. Now, continuing on, turn the page. We want to be able to use this to kind of figure out how good our moderator is. So we could have used lots of things as our moderator. There's lots of plants around the world that use things other than light water like we use. So I'm on the next page that starts talking about moderation, which we know is nothing more than the process of slowing down a neutron. And it says, although logarithmic energy decrement is a convenient measure of the ability of a material to slow a neutron, it doesn't take into consideration those other two things we talked about, scattering and absorption. I want that moderator to scatter the neutron, not absorb. So one thing we can look at is what's known as the macroscopic slowing down power. And it is just a product of the logarithmic energy decrement and scattering. If you look at that, macroscopic slowing down power equals logarithmic energy decrement per collision and the microscopic cross-sectional area for scattering. Either one of these going up means the macroscopic slowing down power, the ability to slow down the neutron, is going up. So these represent things that are a good moderator. What would be bad? Well, what would be bad is anything that was absorbed. So we have to define neutron moderation. Well, we know that's just the product of slowing down the neutron from its birth energy to its ability to get reabsorbed at a slower energy. That process of slowing down and reducing neutron energy level is called moderation. How do we define the characteristics of a good moderator? Another knowledge requirement. One thing would be, hey, have a good macroscopic slowing down power. Have very, very good scattering ability. Have a high logarithmic energy decrement. But this doesn't talk about that third thing. That third thing, if you'll recall, we wanted it to scatter and give off a lot of energy, but we didn't want it to absorb. Aha, let's come over here and look at this thing. Moderating ratio. Moderating ratio kind of takes into consideration all three things. So moderating ratio equals macroscopic slowing down power divided by microscopic cross-sectional area for absorption. Now remember, we're talking about our moderator here. So I want my moderator to have a good macroscopic slowing down power, to be have a good moderating ratio. And I don't want my moderator to have a very good absorption characteristics of neutrons, because then it would gobble them all up. So I want it to have a low microscopic cross-sectional area for absorption. Another way of writing this then is average logarithmic energy decrement per collision, the product of that and microscopic cross-sectional area for scattering. Either one of these two things being high would have me have a good moderating ratio, and I want it to have a low absorption cross-section. We refer to this here as the moderating ratio. Very good. So this defines the characteristics of a good moderator. That's a knowledge requirement. I want it to scatter and give off a lot of energy, but not absorb the neutron. Note, you must recognize our water is a very effective absorber of neutrons. Take a look at this table right here. It kind of compares different moderators. Really cool. So look, we could use helium, or we could use regular water like we do, or beryllium, or carbon, or, hey, looky there, heavy water. Well, let's look at ours. Let's look at water. We see the average logarithmic energy decrement per collision is 0.948. And I just told you it's about 1, and it is. It says collisions to fully thermalize takes about 19. And then look at these characteristics. The microscopic cross sections for water. Well, its microscopic cross section for scattering, pretty good at 103. But we're going to realize in a minute its absorption cross section is way, way, way high, which results in a total moderating ratio, which is our average logarithmic energy decrement multiplied times our scattering cross section divided by our absorption cross section. It equals 148. You can look at the characteristics of helium now and just compare moderating ratio, and you see helium 51, beryllium 159, so it has very similar moderating ratio, but for different reasons. Looky here. It has a scattering cross-section of 7 versus 103, but look at its absorption cross-section. Very, very low. It does not absorb neutrons. So that's why it's such a good moderator. It's not real good at scattering, but it doesn't absorb them. Let's go up here finally to heavy water. Let's go look at the Canadians. Totally different. They take, their average logarithmic energy decrement is twice ours. Twice. So they require twice as many collisions. I mean, it's their energy decrement is half ours. Their collisions is twice, essentially. Look at their scattering cross-section. 13.6 versus ours of 103. And then look, 1/1000th of a barn versus ours. 66 hundredths of a barn. Crazy. Much, much better at not absorbing neutrons. And so therefore, since heavy water essentially does not absorb neutrons, and our water does because our absorption cross-section is so high, look at the difference. 7,752 is the moderating ratio for heavy water versus 148. What that means is they don't lose neutrons to water absorption because their heavy water doesn't absorb water very effectively, whereas ours does. And recognizing that our water absorbs neutrons is hugely important. It affects our reactor a lot. Our water essentially is a poison. A poison is anything that absorbs neutrons and doesn't cause fission. Keep that in mind. It's going to be important as we go forward.